In this video, we'll discuss AP Practice Problem 5. We'll look at the answers and the criteria for getting the points and how to get all the points so you score maximum value in this and get everything you can. All right, so this problem, I think right off the bat, from looking at the picture, you can tell it has to do with regression. Basically, there's a scatter plot, and it looks like it has a somewhat positive, moderately strong linear relationship, right? So I would just observe those things right off the bat, even before reading the problem. The problem's about total race time for the 100-meter dash. They base it on two variables. Basically, it's your reaction time to the starting signal and then your ability to actually run. So from the moment someone, I guess maybe they shoot the gun or whatever they do, from the moment that sound goes off, there's the time it takes for you to even realize I need to start moving. That's usually a very short period of time, but there is a delay, right? Your brain needs time to process and start getting your body moving. And then finally, once your body's moving and you're doing what you do, how long does it take you to finish? So they recorded those. The reaction times are on the x-axis, the running times are on the y-axis. All right, and there's 20 people that this happened for, so you can see, down here are some faster people. This person's pretty slow. They're pretty bad because they have a bad reaction time and they have a bad running time. These people are good. So now you see I have the answer circled there. Part A says circle the point on the graph that represents the runner who won the race and the approximate total race time for that runner. So it's tempting to, I think it's hopefully obvious to pick one of these people. But you have to be careful about which one you pick, because even though this person has the best reaction time, you have to think about the scaling here. This person's actually the best because when you put both of them together, the scaling here is only by like 0.01, where the scaling here is by 0.1. So even though this person has better reaction time, they're actually, they're better by 0.02. Their runtime is actually worse by 0.1. So if you put the two variables together, this is the person who has the best time, right? Even though I said they're a little slower in reaction time, they're considerably faster due to the scaling in running time. So this person's the best. If you add them together, the reaction time plus the running time, you'll find this person is the winner. So, and then they want their time. So you want to circle that point. I think, obviously the way I gave it to you, if you were describing it to me, use the coordinates or something if you didn't have this picture. I would think on this year's exam, they're not going to give you diagrams, so you might have to identify things by another method, all right? So, but anyway, this is the best point. Its coordinates are approximately. I went to try to round, and my rounding actually matched what they had. They allow a little bit of wiggle room on this, but not too much, so don't go too far off. I put 1.52 because it looked a little more than 1.5. I went 9.61 because it looked a little more. And I said, sometimes I'm a little off from their answer, but this was actually dead on to what they got, 9.762. Once again, if you put 1.51 or 0.151 and 9.6, or you put 0.15 and 9.59 or something, so long as they were close, they gave it to you. I think they gave some kind of range, but just don't go too far off. Make sure you read them as accurately. And if you want to estimate them a little better than their scaling, go ahead. So 9.762 is what I got. Something very close to this would get you what you need. So now they say part B, based on the graph, is it reasonable to assume that the reaction time and the running time are independent? I think that's not the case due to the correlation between them, right? There's a linear relationship. It does seem that as people's reaction times go up, their run times also go up, right? It's not just scattered all over the place. It does have this positive association. What we're seeing is as one goes up, the other goes up, right? Higher run times are associated with higher reaction times generally. So since it does look like reaction time and running time affect each other, we don't know if one causes the other, but we do know they seem to both adjust with each other. There could be another factor that's involved, but they're both adjusting with each other. That means they're not independent of each other, right? Like the reaction time seems to be following what the running time does and vice versa. So that's what I put. They don't appear independent since higher reaction times correlate to higher running times. The scatter plot shows a roughly linear relationship. You could use the word associate as well. I use correlate because remember, correlate does say there's a linear relationship, but you could just say associated is probably the better word, because even though these look like there's a decent line of best fit. I don't know if this data continued, if it would curve or something. So either way, you do have to mention something about the linearity of it, or the positive association, the fact that there's one going up and the other going up, and that's why we're not thinking that they're independent of each other. The last one says, based on the least squares regression model, remember that's just a fancy name for the line of best fit. Based on the least squares regression model of the data, explain why the use of extrapolation to predict the running time for a runner whose reaction time is 0.3 seconds might not be appropriate. So extrapolation is when you go, okay, well, here's the trend. I'm going to start using this trend to predict other stuff. The real issue, and we talked about this in class, is this trend is most valid for the data that it's showing. If you go out to someone who has a 0.3 reaction time, I mean, they're off the scale here, right? It's like 0.1 would be over here. You got like 0.2 and then 0.3. It's way out here. The problem is the farther you get from the data, the less guaranteed you are that this pattern continues, right? This pattern looks linear now, but as you go to the right, maybe it flattens out. Maybe it spikes upward. Maybe it curls around or something. I mean, you don't know what's going to happen. So the farther you go from the bulk of the data, the less likely it is that that value is going to be valid. And the main reason for that is because we don't have evidence the pattern continues, right? We know the pattern's working in here because we can see it. Once we leave the pattern, once we go beyond this highest value, we don't have strong evidence the pattern is still there. All right, so it may be still there, but we don't know, and it's possible it isn't, and we don't want to go, oh, we're guaranteed this person would suck at running. We don't really know that strongly. All right, so I had put the value 0.30 is far higher than the max of the data 0.21, like we're way outside the data's maximum. So the prediction may not be reliable, especially if the data doesn't keep its linear pattern shown in the graph for the higher values of reaction time, right? So if this linear pattern doesn't keep up, this extrapolation is going to stink, right? Someone who goes, let's use the line of best fit to predict this person, could be completely off because we don't have evidence, right? All right, so let's see how the grading went on this one. Part A wants a good approximation of the time and you to pick the correct point. All right, so you do both, you get the E, you do one of those, you get the P, and you don't do either, well, you get the I. B wants you to say, well, it's not reasonable to do that, and to mention something about the positive association. So the positive is the key thing. Now, you don't have to actually say the word positive. I said as one goes up, the other goes up. That means positive association, but you have to somehow mention that because what's happening with the data is one thing does something, the other does something. If you point out one goes up, the other goes up, you're pointing out that, look, there's a pattern, and it's not reasonable to believe they're independent since they are somehow relating, if not to each other, to something else that's controlling for both of them. They do say that just mentioning a correlation or association isn't enough. You need to have something about the positivity of the relationship. All right, so this is a little mean, but that's how they are. So if you put both things, you get an E. P would be 1 out of 2, and I otherwise. And then the last part, the part that states that 0.30, you want to say that's outside the data. They did say that they wanted it to be outside of the maximum to actually specify that's on the right side. And so that number one's basically stating that the 0.30 is higher than the max. I'm going to venture to guess that if you just said it was outside, it was far outside the data, they would take it. But it's always good to be specific. It's not too low, it's actually too high, right? So it's way outside on the right side of the data. You want to say something along those lines. And part 2 says states relationship may be different outside that given range, right? So you're stating, number one, the point is outside the range, and then this is the justification. Why is that a problem? Because since it's outside of the data relationship, you don't know if the relationship is continuing. E is if you cover both things, P is if you cover one, I otherwise, and it's got the traditional scaling here that, 3's get you 4, E, P get you 3. Some weirdo combination here is getting you 2. a weak combination, either only one E or two P's is getting you a 1, and then anything less than that gets you 0. All right, so that covers that regression problem. And I believe that's it. I think this is one of the easier problems, but once again, if you don't state enough stuff, it's quick to lose points fast. All right. Obviously, after practice problem 5 will be practice problem 6, so hopefully you'll move on to that. Until then, see ya.